Pressure and temperature of a gas. Wow, pressure and temperature. They sound so different quantities. But are they related in any way? Are they? Yes, the answer is of course a big yes, they are. And this relationship was given by the scientist Gay-Lussac, also called the Gay-Lussac's law for gases. Alright, now Gay-Lussac's law for a gas is also called a pressure-temperature relationship. Okay, so very good evening to all of you, and let's begin with the video. Pressure-temperature relationship given by Gay-Lussac states that at a constant volume for n moles of a gas, at a constant volume is my first thing, n moles of a gas means a fixed volume of gas or a fixed amount of gas, the pressure of the gas is directly proportional to its temperature. Now Gay-Lussac's law is a gas law. Gas law means equating two parameters of a gas by proportionality and keeping other two fixed. Okay, just like what we had done in Boyle's law and Charles' law in our previous videos. You can check them out in our playlist for states of matter gaseous state to get those videos as well. So Gay-Lussac's law states that I am keeping two parameters, volume and amount of a gas, as constant, and I am giving proportionality between temperature and pressure, which states that as temperature is rising, pressure is rising, or as temperature is falling, pressure is falling. This gives us a direct proportionality. So what I can get as the mathematical relationship is pressure of a gas is directly proportional to the temperature of the gas, okay, at constant volume and n moles. That means pressure is equal to constant into temperature. To remove the proportionality, I have to give a constant, which further means that pressure upon temperature is equal to a constant for a gas always. Okay, which states that individually the pressure or temperature of a gas may change, but if I give the ratio of the pressure to the temperature or I divide them, I get a constant. Okay, this was my Gay-Lussac's law, our Gay-Lussac's law in fact. Now coming to the graphical representation of the Gay-Lussac's law, the graph of Gay-Lussac's law is called iso-core. Iso means constant, and what is the meaning of core? The core in this case, if you can just denote iso by constant, and core means volume. That means at constant volume, if I plot a graph, it is called iso-core. Okay, alright, so let's move on to drawing this graph. So if I take the pressure on the y-axis and I take the volume on the x-axis, so pressure in bar, pressure in bar, and I can take temperature in Kelvin here. Okay, and if I draw the graph, I will get the straight line because of direct proportionality, but of course initially the line will be dotted and then will be straight. Alright, now the question is, why is the line initially dotted? Because initial in the Kelvin scale means 0 Kelvin. It is beginning from 0 Kelvin, and at 0 Kelvin, as we had discussed in our video for Charles' law, you can refer to the detailed explanation for that, to that video, that 0 Kelvin is also called the absolute zero, where there is no gas existing because they all liquefy before that. It's a very cold temperature. Okay, so at 0 Kelvin we have no gas, so we put this dotted curve. Okay, rest is same, pressure and temperature are directly proportional, so I'll get a straight line. Now in the books, what we have as a curve is I have got too many lines. I have got this line also with this, I can draw this line also, I can draw this line also, etc. This simply means that I am taking gases at different volumes. Suppose this is a gas at volume V1, this is a gas at volume V2, this is a gas at volume V3, and I am putting the graph for this. But the first graph of course is the main graph, which gives you the proportionality for the gas. Okay, so this was your iso-core of the Gay-Lussac's law. Applications, Gay-Lussac's law from the book, the application given in the NCERT is that pressure of tires. In hot days we find the tires very highly pressurized, whereas in the cold days we find them highly unpressurized because the pressure decreases considerably in the cold days. The application is simply that cold days, as the temperature is less, the pressure will become less, and on hot days, as the temperature is more, the pressure will become more. The basic reason for this is, as I increase the temperature, pressure of a gas is actually measured by the hits on the walls of the container. Okay, this you should already be knowing by understanding the pressure of a gas. It is measured by hits on the walls of a container. So suppose I have a container here, a beaker, okay, which is having gas molecules here, maybe suppose these gas molecules are there, and if I have temperature, maybe suppose 0 degree, okay, then the gas molecules are moving very slowly because temperature is quite low. Now what happens is I increase this temperature to suppose 20 degree. Temperature increases means I have put heat. That means I heat the gases, and once I heat the gases, kinetic energy will increase because heat will increase the motion of the gases and increase the kinetic energy. So the gases will move even faster, and the number of hits on the walls of the container will be very fast, and hence the pressure will be fast. So this is basically the cause of the Gay-Lussac's law, that when I am supplying more temperature in form of heat, in fact, the heat is increasing the kinetic energy, and the kinetic energy is increasing the random motion and the velocity, which is increasing the pressure of the gas, which is measured by hits on the walls of container. So the conclusion here, or the result here, is I am increasing the temperature, which is directly proportional to the heat supplied, which is directly proportional to the kinetic energy of the gas, which is formulated by half mv square. mv's kinetic energy is directly proportional to the velocity of the gas, and this velocity is directly proportional to the hits. More will be the velocity, more will be the hits to the walls of the container, and this is directly proportional to the pressure, which gives me that temperature is directly proportional to pressure. Okay, this is the conclusion with which we will close the class for Gay-Lussac's law. It is very simple, and you can easily calculate with the help of the formula as well. The graph is called isochore because it's at constant volume. In case if you have any doubt, please do write in the comment section, and in case you want me to make up some specific video, please do write in the comment section as well. And please do not forget to like, share and subscribe my channel. With this we close the class. Thank you. Take care.